truth. Okay, today in this lecture, we will discuss the derivatives of vector field. Like earlier lecture, we have discussed scalar field, its calculus and differential calculus. Now, if f is function from S to Rn, this S to Rm suppose, and I will take S as a subset of Rn. So this is a vector form. So image of f becomes vector, then it is called vector field. Now suppose a bar is interior point of this set S. This a bar is interior point of set S. Then derivative for scalar field, we will define derivative of f. This f what will define derivative of f at the point A in the direction of y bar. And this definition is limit s tends to 0, f of a plus hy minus f of a bar divided by h. Like scalar. Only thing is that this f value is vector. And you are taking the line segment from a bar to a bar plus hy bar. So change in this a bar vector to this. This h is a scalar and a plus hy bar is vector. So f value of that difference with respect to what change you have taken, with respect to h change you have taken. So that limit exists, then it is called derivative of f, and it is vector. This is a vector. Huh? If f is scalar field, then it is scalar. So derivative of f at the point a bar in the direction of y bar is the meaning of this. So this is the definition of derivative which we have mentioned here. Now see what happened. For example, suppose f is function from S to Rm, and S is a part of Rn. And if you take the point x bar as x1, x2, xn, then the image of this x bar is a vector like this. So suppose it is f1 of x bar, f2 of x bar, and fm of x bar. So this is each one is the scalar. Each one is a scalar. Likewise, I will define example of, suppose I will define R2. Okay, I may not take R2 in general, and R3. So as per R2 is concerned, the point xy is like this. So what is f of x bar meaning? F of x bar meaning is f of x comma y, and let it defined by this x plus y. I will take simple algebraic function which always exists for every value of x and y. That's why I choose domain function as R2. So look at this. This is the first function, and this is second function. And you see x and y are real number. X plus y is real number. X minus y is real number. So each component is scalar, and this tuple component becomes vector. So I have to define in R3. So I will take product x y as last term. So this is f3 x bar. So because of these three, you must define like the pattern of R3. That is, there will be three component for it. So this is vector value function. Now here, the definition of derivative of f at a point A at a vector A in the direction y. So in this book, the notation of vector is not used. As per vector is concerned, the bold letter is used, and as per scalar is concerned, not bold font. So keep that in mind. Else, while writing, I will put bar on the vector. So derivative of f is a vector in Rm. This is important statement. Derivative of this f, the derivative f dash a bar semicolon y, that is f dash in the direction y, is vector, and that vector is from codomain, and codomain is Rm. Now we discuss the component weights. Suppose Fk is the kth component of that function, and if f dash ay exists, the important statement we are making, suppose Fk x bar, this is the kth component of f of x bar. Like uh, we have in the codomain total m component, f1, f2, fk, and fm. Then the derivative fk at a point a bar in the direction y bar exists. It means for every k, this is for all k. If this derivative exists, then f dash a bar in the direction y bar is also exist. So each component's derivative, you are creating the scalar. So how this fk is a function from s to r. Fk is function from s to r. So each f1, f2, fm are the scalar valued functions. And writing combining in the tuple form, it becomes a vector. So if like a scalar, as we are discussing in the earlier lecture, thus derivative of scalar vector field. So each component's derivative exists, then its derivative exists. The mention statement here. Fk is the kth component of it, and we denote derivative exist. We note that this derivative exists if and only if every component's derivative exists for k equal to 1 tm. So in this case, how you write? In this case, we write f dash of a bar in the direction y bar as f1 dash a bar in the direction y bar. First component f2 at f2's derivative at a bar in the direction y bar. fk dash, and since there are total m components in the direction y bar. So these are the k components, m components, sorry. So this must be part of codomain, that is Rm. And whatever a bar and y bar you are choosing, they are the part of Rn. They are subset. They are part of S, and S is subset of Rn. The region S on which F is defined. It is not necessarily defined for whole of Rn. At some point, it may not exist, so that's why the specified S is mentioned there. So if component derivative exists, we call there as if y bar is unit vector, we call it as each scalar component will be the directional derivative of f1 in the direction y bar. Similarly, f2, fk, and fm. So the general derivative is written here as a component wise. Okay. And since we may write this as f1 dash, since it is a scalar value, and I will take 1, 0, 0, and last. Similarly, f2 dash, I'm adding with this 0, 1, 0, 0, 0. So these are the unit vector. I am writing expressing in terms of linear combination. So okay, I'll write fk's. Fk dash a bar comma y bar. At the kth place, you write 1. This one is kth place. And the last term, fm dash, it is 1. So these are the vectors. So I may write in the summation form. Summation fk a bar in the direction y bar of ek, and k running from 1 to n. So what is this? This is derivative of f at the point at the vector a bar in the direction y bar in the form of linear combination. The sum is running from 1 to m, since there are m components. Sum is running from 1 to m. So, and for each scalar quantity, you know how to calculate it. For each of k, you can calculate easily. So in this way, this will become a vector f dash a bar in the direction y bar. The summation is mentioned here. That ek is the kth coordinate unit vector. That ek is kth unit coordinate vector. Now, likewise, scalar field. Likewise, scalar field. Here also we say this vector field f is differentiable. Likewise, this scalar field here f is differentiable at the same interior point whatever you have chosen here. If there exists a linear transformation, this is important statement. The condition of differentiability, you may treat it as definition. F is differentiable at interior point A if there exists a linear transformation induced by this A from Rn to Rm. Now that S may not be vector space. Whatever domain mentioned here, it may not be vector space. As per concerned linear transformations, you should choose vector space. So in general, Rn is vector space and Rm is also vector space. So TA map induced by A will be defined like this, and this is the Taylor's formula which we have defined in the scalar field. So if such TA exists and this scalar function EAV exists, who is tending to 0 as vector change to 0. If this is holds, then this F vector field is said to be differentiable. Okay, I will write definition here. F is said to be differentiable vector field. You can write side by side. Vector field F is said to be differentiable at A bar if there is linear transformation if there is a linear transformation TA from vector space Rn into Rm such that TA from Rn to Rm. Okay. I have written repeat statement, so I will erase this such that we have to write Taylor's formula here. Such that F of A bar plus V bar. This is nothing but F of A bar plus what you write there? The linear transformation at V bar plus norm of V, and this is the scalar value function EA bar V. This E function is such that when norm V tends to 0, it will tend to 0. This is a scalar tends to 0 as vectors norm tends to 0 scalar. Norm is always scalar. Or you can write norm of V is less than R. R is positive small number. Okay. This EAV is a scalar in the scalar vector field. But in a vector field, this should be vectors. So I have called it as a scalar, but it is not a scalar. This is vector. Sorry for that. This is vector. If it is scalar field, then it is scalar. In example, we can understand easily. EAV is vector from Rn codomain. This is vector in Rn. And since that V is vector, but norm is scalar, so E vector multiplied by scalar. Because what happened? You logically you can think this quantity is vector from Rm. This is a vector from Rm. This TA is vector space from Rm to Rm. So this is vector. So how could it will be scalar? You cannot add vector to the scalar. So this quantity must be vector in Rm. So and so we can add these three quantities. In that way, you can think. So differentiable means it should satisfy that Taylor's formula. Now in the scalar field, we have proved that this TA, thus this TA is f dash of a bar y. Likewise, we can prove here also because whenever you write vectors, each component must be a scalar. That is important. So I will take next result related to computation of this TY. Okay. I will write theorem statement here. Assume F is differentiable means that Taylor's formula holds. Assume that F is differentiable at A vector A with the total derivative, notation of the total derivative. So while writing suffix, you don't put bar there. So that TA is called total derivative, that linear transformation. Then the derivative which we have defined. What derivative? F dash at A bar in the direction Y bar. The derivative which we have defined, it must exist. It must exist for each and every vector of Rn. And that derivative is given by this formula. This formula is important. The derivative is given by f dash at A bar in the direction Y bar. Moreover, if you write this as a component wise, moreover, if your F is like this, first component and M component, and Y is from domain. Then what is the value of this TAY? So it should be summation K from 1 to M. It is a dot product of gradient of each component of F with YEK. YEK means what? If K is 1, then Y E1 is just Y1, like that. The kth component of Y. The meaning of this is kth component of Y. Okay, this quantity is vector and multiply by ek. That is kth component of this. Okay, another form I will write this as. So what is means? So what is the first component? If k is 1, if k is 2, if k is k and k is m. So you know, you see each component dot product of this vector. So this value is scalar. This value is scalar, and your ek is vector. So kth component of this TA of y, that meaning of it is this. So okay, we'll prove this. Statement आलं लक्षात काशिफ? Okay, we'll go for proof. We'll make case if y is 0. If vector y is 0, then what will happen? F dash of a bar in the direction y bar by the definition of limit. It is limit s tends to 0. If you put y bar equal to 0 here, what will happen? F of a bar, F of a bar will cancel, it will become 0. This is one side. And what is T of a y bar? In the any linear transformation, image of 0 vector is 0. So this 0 vector is from Rn and this 0 vector is from Rn. So we have to assume compulsory y not equal to 0 and then we'll think. If 0 holds, then equality holds for this. Now let us assume that y is not equal to 0. Second case, this vector y is not a 0 vector. And we take a vector v bar as hy bar. That hy bar you are writing the notation. We take vector v bar as hy bar in the Taylor's formula. Since it is differentiable, Taylor's formula holds. So f of a bar plus b bar, instead of b bar, I will write hy bar. F of a bar plus b bar, I will shift a bar to other side. I am writing this because f is differentiable. Differentiable means the Taylor's formula holds. So this is equal to T of v. So I'll write T of hy bar, norm of v. So I'll write v is hy. So I'm putting v equal to hy there. I'm putting value of v as hy. So here it is hy. This value is norm of hy. Okay. And this is multiplied by vector quantity EAV. Okay. And this EAV tends to 0 as v tends to 0. What do you mean by v tends to 0? Okay, here we'll divide it by h to both sides. In the next step, I will divide by h. I will divide by h. I will divide by h. Okay. So since it is linear transformation, since it is linear transformations, this scalar h will come outside and cancel with the denominator h. Here norm this is also scalar. I will take, okay, I will write in the next step f of a bar plus hy bar minus f of a bar. We are defining like scalar T of y bar plus, so mod h will come outside and from the norm. So more as h tends to 0, the mod h upon h will be plus or minus 1. But when h tends to 0, hy bar is also tending to 0. That is, you are taking norm v tends to 0. So when you letting limit h tends to 0, it means norm v tends to 0. So limit of this expression is f dash of a bar comma y bar. Since h tends to 0, if you approach from positive side, it is plus 1. If you approach from negative side, it is minus 1. And this quantity will tend to 0 when norm v tends to 0. As h tends to 0 means norm v tends to 0. So whole expression becomes 0 whether it is multiplied by plus 1 or minus 1. So in this way, when y is not equal to 0, you have proved this. Like scalar, here also we have proved for vector. Now moreover part is important. So the moreover part is that f dash of a bar y, this is, as I have written earlier, component wise k from 1 to m. It is fkth component a bar at y multiplied by ek, and the sum of all these. So this is the for scalar quantity. As from the scalar calculus, this is nothing but del fk at a bar. That is the proof of this. K from 1 to m del fk a bar y. Another formula for f dash you can compute like this. So it is a proof of this result. I'll mention in the remark as the matrix form. Any linear transformation can represent matrix form. So this TA of y bar is nothing but total derivative of f at a point A y bar. So how this written in the matrix? Since transformation is from Rn to Rm, matrix must is of order dimension of codomain by dimension of domain, as we have seen in the linear transformation matrix. And the whatever matrix you write for this, it is called as Jacobian matrix. How one can find this in the matrix form? What d f of a bar. We'll write this matrix here. So derivative with respect to first component of first vector, first scalar, f1, f2, fk, f1, f2, fm, you are going to write. So f1's derivative with respect to second component, f1's derivative with respect to, how many components are there total? How many are there variables with respect to first variable? With respect to total n variables are there. Similarly, second column is used for derivative with respect to second variable. So d2 second, this is d2 of d1 of f2 a bar, d2 of f2 a bar, and dn of f2 a bar. And the last is for the mth component, first derivative of m component with respect, not first derivative, m components derivative with respect to first variable x1, suppose mth components derivative with respect to second, and mth component derivative with respect to nth. This matrix is referred as Jacobian matrix. This matrix is called as Jacobian matrix. It is Mn partial derivatives. So with respect to this, your Taylor's formula becomes f of a bar plus b bar is nothing but f of a bar. And instead of this, I will write f dash at a bar of v. Instead of y, I'll write v plus norm of v. This will tends to 0 as norm v tends to 0. This f dash a v is nothing but the matrix product of dfa with v. V is a column vector, dfa with v. And in the next lecture, we are going to discuss how differentiability of vector field continues with implies continuity of that vector function. If a vector field is differentiable, then it must be a continuous there at whatever point we choose. Okay.